Section 6.6, exponential and logarithmic functions. So this is the section where we kind of get into the algebra of solving logarithms and exponentials. So I mentioned last section that it's kind of an introduction to this section, and honestly the very first section that we talked about logarithms is also going to be used heavily. So if you didn't feel comfortable about translations or maybe how to compress logarithms, it might be worth reviewing that before diving into this section. Now the first thing we're going to talk about is solving exponentials, which at least for starters have almost nothing to do with logarithms. We're going to kind of use a neat little trick to solve them. And this neat little trick is that if we have the same base of an exponential, then we can set the powers equal to each other and then potentially solve from there. So for example, I have 5 to the 2x is equal to 5 to the 3x plus 2. All those bases are exactly the same. I can set the powers equal to each other, and then I can just solve from there. I would subtract both sides by 2x. I subtracted 3x from both sides. Then I would divide by -1. I would get x is equal to -2. And we can go ahead and check this answer. It's not that hard with an exponential. I think we'd have to have a calculator because we'd have to evaluate 5 to the 4th at some point. But it's worth checking, and then eventually when we get into logarithms, you will have to check it. Otherwise, you could have extraneous solutions. Now, sometimes it looks like we can't really solve it with this trick, which is true for now. I don't have the bases equal to each other. One of my bases is 25. The other one is 5. So I can't just set the powers equal to each other. But those look like they're kind of related. Like when I see the number 25, I think, okay, there's a lot of things I can do with 25 when I start thinking about 5. And so if you kind of see maybe this vague relationship, then you can start talking about, okay, is there something I could take the power of 5 to in order to get 25? Or maybe if I could reduce it to a lower power and then get it up to 25 like that. So in this case, long-winded way of saying, 5 squared is 25. And so what I can do is I'm going to leave the 5 alone on the left side, but the right side I'm going to say, okay, I don't actually want to deal with 25. I'm going to say 25 is equal to 5 squared. So I can rewrite the right side as 5 squared, and then it's just times 3x plus 2. So now I actually have like bases. I just have to distribute the 2 to the power. So 2 times 3x is 6x, 2 times 2 is 4. And now I just do exactly what I did in example 1. I set both things equal to each other. I subtract 6x from both sides. I divide, I get x is equal to -1. And then again, if I want to check my answer, good idea, not super difficult. I would just plug -1 into my original equation, and both sides of the equation should be equal to each other. Now, this is where we're going to start to bring in logs into the equation, because honestly, probably the main reason logs were invented were to kind of resolve the scenario of saying, okay, I want to solve this equation. I obviously can't divide both sides by something or subtract things from both sides in order to get x by itself. So in order to undo my exponential, I'm going to use a logarithm. So I'm going to translate 5 to the x is equal to -100 by moving that base over to the other side and saying x is equal to log base 5 of -100. Or I could use the fact that when I'm dealing with an exponential, I can't have a negative result, because an exponential's range is 0 to infinity. So that would be a graph kind of that swoop that goes up to the right side. So I would get no solution. If we wanted to kind of continue with my line of thinking with my logarithm though, very similar logic. I would translate it. I would get x is equal to log base 5 of -100. I can't have a negative input with my log, so I would also get no solution. So it's either that, like, I guess when I did this in my notes, I thought, okay, let's talk about the range of an exponential. Honestly, if I saw this problem outside of my notes, I would probably take the logarithm and then look at the domain of that. But that's something to be aware of. It's kind of logs and exponentials have this similar flavor to absolute values, that if you see a negative somewhere, there's a decent shot something weird's going to happen. So maybe pause and think about domain and range before you go about solving and getting a straight up answer. Okay, this question, 2 to the x is equal to 3 to the x plus 1. I can't really use the trick that I saw in the last slide because there's not really anything I can take 2 to the power of to get 3. I mean, there is technically something that exists. It's not a really nice number that I could figure out quickly or in a reasonable amount of time or anything like that. So this is one of those kind of weird problems that there's a lot of different ways to solve it. You might see something on the internet that's a little bit different for what I'm going to do. And honestly, your answer might look a little bit different as well, but it has potential to be right because logarithms are, maybe if you compress it a little bit further or expand it or use change of base, it can make things that don't look like the same thing are actually the same thing. So a good way to kind of check your answer against mine or WebWorks or something like that is to honestly just throw it into your calculator and say, I don't think these things are the same. Let me check. Oh, I got the same number, so they actually are the exact same thing. So the process I'm going to use is, since I don't have like bases, I'm just going to take an ln of both sides. I'm not really doing anything in that step, but I'm kind of just following that golden rule of algebra that I can do something to both sides of the equations as long as I do it to the other side. Like I can't just ln one side and not ln the other side. So I'm just doing the natural log of both sides. You could do the log regular base of 10 of both sides. Honestly, you could translate immediately as well. So that's kind of what I'm talking about. There's a bunch of different ways. This is just kind of the way that I believe our department prefers. This is kind of the route that they like to do. And so what I'm able to do if I take the ln of both sides is I can use that power rule and bring the x in front of, bring the powers in front of both logs. So if I use the power rule, ln 2 to the x becomes x ln of 2, and ln of 3 to the x plus 1 becomes x plus 1 times ln of 3. And now I just kind of solve using algebra. I guess I repeated the line again. That's weird. Okay, so now I'm going to solve using algebra. I'm going to distribute my ln of 3 to x plus 1, so that becomes x ln of 3 plus ln of 3. Now I want to solve for x, so I'm going to subtract x ln of 3 from both sides. I'm going to factor out x. I'm going to divide both sides by ln of 2 minus ln of 3, and that gets me my final result. So I could potentially, if I wanted to, compress that denominator. It's one of those that again is still technically correct, but anytime you can do less work in mathematics, or at least when you're doing a test and you're stressed about the final, if it doesn't say like compress anything or anything like that, I would not do the extra work and I would just leave it like this. But another answer just off the top of my head would be if I had logs there versus ln, or another equivalent answer is ln of 3 over ln of 3 divided by 2, or no, 2 divided by 3. So if you're getting those different answers, like I mentioned, just go ahead and throw them in your calculator, see if they are getting you the same number result that I just got in this example. Okay, now we're kind of leaving the log world for a little bit. We will see logs later on in this example. Never mind. So at least for a starter, though, we have exponentials here. And so in order to kind of solve this exponential, I'm going to try and get I'm going to get all of my e's on one side and all of my numbers on the other, which is just a one-step process in this. I'm going to subtract e to the 2x from both sides. And then anytime I have an exponential, usually my goal is to get that exponential by itself. So I'm going to divide both sides by 6. I kind of did two steps here. 3/6 reduces to 1/2. And then if I translate e to the 2x, I will get the ln of 1/2. Divide both sides by 2, I get x is equal to ln of 1/2 divided by 2. Now this one's a little bit more complicated of an example because the powers aren't the same. So in the last one, let's go back to the last slide. Notice how I had e to the 2x, e to the 2x. So when I subtracted e to the 2x from both sides, I was able to combine them into a single exponential. Where here I have e to the 2x is equal to e to the x plus 2. So in this case, I'm going to actually get everything on the same side because I can't really combine those guys. And then this looks awfully like a substitution problem because I have a trinomial. Seems like maybe I could factor it, maybe not in the form that it is right now. But if I say u is equal to e to the x, well, I can rewrite my problem as u squared minus u minus 2 is equal to 0. I factor that. Two things that multiply to get me -2, add to get me -1, -2 and 1. I solve, and so u is equal to 2, u is equal to -1, but I'm not solving for u, I'm solving for x. So I plug back in e to the x, and I think I solved that, yeah, okay. So I plug back in e to the x, it's equal to 2, I translate it, so x is equal to ln of 2, great. I plug in e to the x, it's equal to -1. Well, now if I translate it, I would get x is equal to the ln of -1, which is no solution. I can't have a negative input for my log. Or if you feel really comfortable with exponentials, we mentioned on our previous slide that if I have an exponential, I can't really have that equal to a negative number because that number is not in my range. Again, I kind of prefer the log logic, but either way will work. Now getting back into logarithms. If I have a logarithm and I kind of have some other stuff lingering around, I want to get that logarithm by itself. So I'm subtracting 6 from both sides, get ln of x is equal to 4, and then this is just a simple translation problem from there. Ln is the natural log, so that's a log base e. If I translate that, I would move the base over, I would get x is equal to e to the 4th. Very similar concept with this question. I have 2 times ln of x plus 1 is equal to 10. I divide both sides by 2, and then now I have my logarithm by itself. It might not feel that way because I have an x plus 1 in this case, but that x plus 1 is in parentheses. Not really even in parentheses. It's my input of my logarithm, so I can't move that -1 over. In this case, I'm going to translate at this point, so it would become x plus 1 is equal to e to the 5th, and then I would just subtract 1 from both sides. Now here I have logarithm. Again, I'm going to get a logarithm by itself, and the nice thing about this question is that they have the same base. They seem like they don't have a base, which means they have a log base 10. So I'm going to add the x minus 1 to the left side of the equation. And since they have the same base, now I can kind of use those properties we saw last section. I can compress it into a single log. Because right now I can't really translate it. If I have a plus or a minus in the middle or in between the two logarithms, I don't really have the logarithm by itself. So I'm going to compress it until I have a single log, which would be x plus 2 times x minus 1. And then I'm able to translate it. So I can translate my log, which has a log without any base is log base 10. So I translate that to move the base to the other side. I get 10 to the first. And then I FOIL, so x plus 2 times x minus 1 gets me x squared plus x minus 2. 10 to the first is 10. Subtract 10 from both sides. Factor. And then I get x is equal to -4 and x is equal to 3. Now with logarithms, we have to check our answer because it wasn't that important with exponentials because an exponential has the domain of everything. So if you solved it and you're able to kind of get to the end, and you did everything correct, your answer will work. With logarithms, your domain is not everything. So we're going to kind of go back and we should plug it into the whole equation. But at any point, if we have a negative input for a logarithm, we know the answer doesn't work. So I think I checked x is equal to 3. I plugged it in. Log of 3 plus 2, is that equal to log 1 minus log of 3 minus 1? Is log 5 equal to 1 minus log 2? I added log base 2 to the other side and compressed it, so log of 10 is equal to 1. And so 1 is equal to 1, so x is equal to 3 works. So now let's check -4. So if I plug in -4 in for the x's of my logarithm, So now let's check -4. So let's plug in -4 into our original equation. So I replace my x's with negative 4s. And so I would get a log of negative 2 is equal to 1 minus log of negative 5. Well, alarm should kind of be going off in your head ideally at this point. I have an input of a negative logarithm. I can't have a negative input for my logarithm. That's not in my domain. So I actually don't have to go any further in my checking. I can say negative 4 is not a solution. So I just kind of cross out that negative 4. And it's worth mentioning again that if you're taking a test, I don't want you to kind of erase negative 4. I don't want you to like scratch over it completely. Just put a tiny cross through the equal sign showing me that you know that that is not a solution that works. Okay, now into an application question, and we'll see this application question in the next section. So I wouldn't say you'd have to definitely track through the whole process, but maybe try and do your best to understand the majority of it now, and then maybe when you see it again the next round, you'll feel a little bit better. So exponentials are really good at kind of modeling the decay of a material, specifically kind of chemicals or compounds or molecules. And so in this case, we're talking about a sample of uranium, and it decays, if you can kind of imagine the flip of an exponential. It's one of those that decays very quickly for a while and then kind of sits around for a really long time. So we do use an exponential. We tend to use the exponential e when solving equations like this. So it's a very good way to do this. And if you've ever heard of decay, chances are they're going to be using a very similar formula to this. So the radioactive decay formula has my function, I'm just going to call it a of t, is equal to a with a 0 subscript, or we call it kind of a naught, times e to the kt. And so a naught is my additional amount, how much I start with. T is time, usually years unless it otherwise specifies in the question. And k is my growth constant that sometimes we're given, but usually we kind of have to do a little bit of work to find. So to answer this question, that's exactly what we're going to have to do for starters. We're going to have to find that k. So I'm going to find that k by plugging in the information that I have. I know my initial amount is 1,000. I know my half-life is going to be 103,800,000 years. I don't know if that's technically correct, but I think I pulled that from somewhere. It's good enough for this example. And then half-life is something that we talk about a lot with decay. We talk about half-lives. You may be able to kind of guess what it means. It's how long it takes until half of the material is gone. And so we can talk about 2 half-lives because that would actually be how long until 3/4 of the material is gone. Half of the amount and then another half. So it's a very popular term when we're talking about decay, and all it means is how long will it take for half of the material that I have to disappear. So I plugged in that information, right? My initial amount's 1,000. My time is the 103,800,000, and that is going to be equal to 500. That's half of the amount that I started with. And now I just solve this. So I divide both sides by 1,000. I reduce. I translate, and then I divide both sides by that large number, 103,800,000. And now what you should do is you should probably kind of figure out what that is as a decimal. I think it's a really, really, really small decimal, so I just left it in this form when I'm going through and solving. But if you want to, you can kind of find the decimal and then plug it back in the equation like we're about to do now. So now that I have my k, I can start to try and answer my question. I want to find when 20% of my sample of uranium has decayed. So in this case, my initial amount's still the same. I'm starting with 1,000 grams. And now I'm trying to find time. So I have my growth constant here. It's kind of a gross thing that maybe could use some simplification, but I have my growth constant now. And I know that I will want 20% of my original material. So now I plug that into my equation again. I have my initial amount, 1,000. I want to find how long it'll take for 20% to decay. So I will have, after 20% decays, 80% of the original amount. So 0.8 times 1,000. And then I plugged in my k, and I'm trying to solve for t. So I divide both sides by 1,000. So 0.8 is equal to my exponential. I translate. So my e becomes an ln of 0.8, and now I'm just left with the power. And it's kind of easy to lose sight of the fact that that is e to my really gross k to the t. So that whole thing is a power. So what I just did is I undid the exponential, and now I brought down the power, even though it looks gross and it kind of seems like I'm multiplying. No, that is the power of e, or it was the power of e. I divide both sides by that growth constant, that k. And since I'm dividing, if I'm dealing with a fraction, I flip and then multiply. So doing that, and then now is kind of the time where I threw everything in my calculator and found that t was 33,416,136.24 years. That's the end of the section.